the subject. So I think the lecture should be well suited also for beginners, at least for talented beginners. So we will at the beginning go through the very basics of programming in a bit abstract, let's say abstract point of view. So basically we will start at the very basics, like what's a variable, how program control flow works, etc. And then we will quickly take a look onto the low-level aspects of it, so how these things are represented inside the computer, how the computer is able to do what it is doing, so how variables and different control flow structures are processed. This should be quite enlightening. We will during this also take a look on the assembler side of things, so what machine commands the C or C++ compiler generates from the C++ source code that we are providing it. I know this might be a bit overwhelming, but don't worry, the assembler part of things is just for your curiosity. It is not, you will not need to write anything in assembler, at least I don't think so. And it will also not be like tested in any way if you know the assembler side of things. It is just good to have seen that at least once, to develop some understanding of how the things that you do in C++ really are then interpreted by the computer, mainly because it also helps you later to avoid different programming mistakes that in C or C++ can be quite common. So I think this low-level view is interesting. Now, if there will be demand for it, we can go in more detail on these subjects. So if you're interested in the assembler side of things, we can commit a few more lectures to those things, but we will see how quickly we'll progress and what the general skill level in this group is. Yeah, so since 5 minutes of waiting have passed and it doesn't seem that many more people are appearing, so let's go through the attendance list. What's the quickest way to do it? I will just compare the list against the one. So I'll just go by the, since every one of you I think entered their full names into the Zoom, I think this is the quickest approach. So I will not need to like call everyone like in the physical lecture. I will just go with the digital version. That will take a minute or two since we are almost 31 people. Okay, someone has troubles reconnecting. That is not good. Well, I mean, restart Zoom. That's always an option. Try a different PC maybe if you have one. I don't have any other advices to give since it's just a paid-for platform that the university is probably paying a lot of money for, but it's completely out of our control. So if the connection doesn't work, try updating the Zoom client maybe. Updating the Zoom client might work. Well, anyhow, I will go through the list now. Is that ordered in any particular way? It is not very user-friendly. So the list that the system here is not sorted alphabetically. Well, you know what? I will just make a screenshot of the attendance list and check it later on. I think that is the best solution for now, since this avoids any waste of time. And there are still a few more things that you will need to, that we will need to do at the very beginning in order to start the lecture. So what we need before everything will be a development environment. So you already see my screen sharing. So what I have installed and what you will also need to install is Visual Studio. I here have the version 2019, but you can also go for the version 2021. Actually, we might go through the process of installing it anyways, just for the sake of demonstration. So you open some web browser, go to well, you just Google Visual Studio. I'll post the actual link. Oops. Into the chat. It is from Microsoft. It is free. At least there is one of the editions that is free. It's called Community Edition. So here you go on this website that I posted in the chat. So I hope all of you have a Windows PC. If you don't have a Windows PC, you will need to run a virtual machine or something like that. Oh, apparently there is a Visual Studio for Mac. That's new. So if you have a Mac, just go for the Mac. If you have Linux, then you probably have a Windows virtual machine anyways. So you go here, click on Community Edition. Well, I will go with the... which one do I have the license for? I think for the Enterprise one. But they are almost the same, so it's not really a large difference. You save the installer. Then you open the installer. Is everyone following so far, or should I be slower? Now is the time to say. Okay, no questions, no one is saying anything. But you can hear me, right? Yes, okay. You need more courage to speak up. Okay, so anyhow, we allow the installer access to the internet and administrative permissions. That will take a minute or two. Well, that should be quicker, but okay. So what we will need is here, where is it? Desktop-Entwicklung mit C und C++. This should be shown in the language that you natively have on your system. I would definitely recommend to just install the English version, because if you then Google a problem or an error, or even Google how to do something, and then they are guiding you from a large amount of menus which you don't know by heart, the internet will give you to 90% results in English, probably. Or at least if you Google for the issues in English, you have the biggest chance of finding a solution. So I always install the English version of Visual Studio. And as I said, you need this Desktop-Entwicklung, so that will be desktop development with C++. And from the side thing is here, what shall we also select? These and these and these and these, and that is not. Yeah, these are also good. Sticker, what do we need that for? We probably don't need this, but why not? No, we don't need that. Okay, wait. 64. Let's see. I will make a few screenshots and post them into the chat shortly. So this. Yeah. Okay, so on the workload screen, that is actually quite nice. So can I paste that into the chat? No, I cannot. I cannot paste images into the chat apparently. So does anyone have this screen open? If so, and you have selected this, then select the components as shown here. No, so IOT and Android tools are not required. Net applications are also not required. Also, if you have a question, just speak out loud instead of writing in the chat, because I think that is more... well, it will grab my attention faster than the chat that I may not have on my eye. So I have like one screen that you are looking here, then another screen above it, then another screen to the left of it, and then two more screens. So it's easy to lose a window.
Okay, thank you.
Okay, so now let's again. So for the other components, which we might need or might not, depending on your set of interests, you go to the einzelne Komponente page and just type Neueste, and then select all the things that are without spectral mitigations, because we don't need that. And if you then go to the other screen again, then it should give you this list of additional components. Is everyone so far? Can we continue? Here? Do you see it now? Mm-hmm. Gut. So while you are all selecting those things, maybe a short information of what Visual Studio actually is. So Visual Studio is called a ID, so Integrated Development Environment. And the idea is that it combines a text editor, a debugger, and a compiler toolchain all in one product. So what those things are, a text editor is pretty self-explanatory. It's just something that you use to write the source code. Of course, in case of more specialized editors, it has a lot of additional features that normal text editors don't have, like that it highlights syntax mistakes, highlights the syntax as such that it makes code more readable. Many of them, including Visual Studio, offer you some sort of autocomplete, which sometimes is helpful and sometimes is more annoying than it's worth. So I guess that's a very personal decision whether you want to use those autocomplete functions or not. What else? The next thing, the debugger. So when you write maybe we should take the debugger as the last thing. The compiler toolchain. So when you write some source code, there are different ways how the computer can come to executing your source code. So the most basic types are just compiling the source code to machine code. So this is what C and C++ are doing. So in this case, the compiler takes your source code and is generating a binary program that the computer's CPU can execute directly. In case of C and C++, you have two distinctive steps. First is the compilation, and then there is the linkage, which I'll explain later. The next type of execution is compilation to some sort of intermediate representation. So, for example, all these .NET languages like C# are doing that. What else? Java is a very prominent example of such a intermediate language. And the idea here is that the source code gets processed by the computer and put in a representation which allows for a very efficient execution, but it is not directly represented as machine code. The advantage of such an approach is that you can use the same binary on different architectures. So you could write a program in, let's say, C#, and then you could execute it on a x68 Intel computer, as well as on some ARM-based thing like one of these new MacBooks with an ARM CPU. And in both cases, the execution performance will be comparable. In both cases, it will not be as good as native performance, obviously. Although how close it comes to native performance to a large extent depends on how this step from executing these intermediate representations then to what the CPU actually does is implemented. So in the simplest way, it is really just it reads the individual instructions, and then it needs a lot of machine commands to execute each of them. But there are also approaches where this intermediate representation is then, at least in parts, compiled into machine code representation, but this then happens on the machine where this code is executed. In contrary to C and C++, where the compilation step is directly up to the machine code is done on the development computer, and you deploy only the final machine code. The third type how your program code can be executed by a computer is interpretation. So basically you have the text that makes up your machine code, and it is just in real time parsed, and then the computer does whatever the current line it's currently executing tells it to. So the most prominent example of this would be, for example, BASIC, that some of you may have heard from something like very old computers use BASIC, for example. More modern examples are JavaScript. Although with JavaScript it's technically it depends on which JavaScript engine you are using, because like in the good old days, all the execution of JavaScript, it was just interpretation, but with more modern JavaScript engines, like especially Google's V8 engine, it compiles the JavaScript then in real time on the target platform into machine codes, into machine opcodes, and this is quite efficient. So with some extensions to the normal Java language, this allows the performance to be so how to say it? It's 1.16 in comparison to native code. So it needs 60% more time to do the same thing that a program written in C would need. At least in specialized test cases. So there of course are use cases where the performance is even with this compilation really terrible, but in optimized case, so for example if you do some cryptographic operations or some mathematical operations that can be nicely compiled, then it is really good. Where this breaks down is if you have interactions between the written code and the environment, the Java environment around it, because then you have to go through multiple levels of bindings, such that whatever this script tells the computer to do. So in the end, the script needs to interact with some native API, and this transition is usually there quite inefficient. So these are the three types how a computer gets to execute your source code. And since we are here, we will be looking into C and C++. We will really just look into the compilation directly into machine code. And the thing with compiling and linking, so when you compile something in C++, the way this is implemented is that from every single source code file that you have will be an object file generated, which has already a position independent machine code representation of what this source code wants it to do. But of course then you want to connect multiple of these files together so that they can interact. You will need some libraries, some static libraries, a C runtime environment, etc. And those things are all put together into one binary file during the linking stage. So this is these are the two. Sorry, I have to pick up. Sorry about that. So yeah. What else is the third thing I mentioned, but for that, is anyone ready to click on install? If you are, then just do it, and while I'll continue talking, the installation should be running and installing. I see a few more people has arrived, so I'll make a new screenshot of the attendance list. Okay, so the third thing I mentioned, what a IDE makes up, is the debugger. So the debugging as such is the process of finding programming mistakes, or more generally speaking, finding out what your program is doing while it is doing it. So the most typical use case would be, or maybe I should start from another side. Let's first say how the debugger works, and we'll say how to use it. So the debugger is a tool that allows you to interrupt the program execution and inspect the internal states of the program. So when the program is running, or before it is even running, as soon as it's loaded into memory, you can use the debugger to set so-called breakpoints, which are basically in the machine code you replace single instructions with a instruction that tells the CPU to raise a specialized exception, and this then tells the debugger that this breakpoint was reached. And what the debugger then does is it replaces the instruction with the original instruction again and continues execution. At least this is how it works in with languages that compile to machine code. Of course, if you have something that is interpreted by an interpreter or compiled into an intermediate language and then executed by a virtual machine, then you have much more convenient ways of debugging your program. But from the user's perspective, how this works under the hood is not so relevant, because it mostly works always the same. We just are setting a breakpoint, and when the execution reaches this breakpoint, it is stopped, and the debugger tells you arrived at breakpoint such and such, and what do you want to do? If it's a program that you wrote yourself, then the debugger will show you the line in your source code where the breakpoint was triggered. There are ways in Visual Studio how you can configure it such that you could even edit the machine code and then let the program continue execution. But in my experience, this is quite error prone, so I would not do that. And you can of course see the contents of all your variables. And then you also can do is you can step through the program step by step, or in this case, let's say line by line. Or you can tell it to execute until you exit the function and things like that. So this is quite flexible. What debuggers also can do is if there is somewhere an exception thrown in your program, so if there is a programming error that is caught by the CPU itself, so the CPU encounters some condition where it cannot continue, like for example a memory access violation, so it tries to read a memory which is not there, or it tries to write to a memory which either is not there or is read-only and stuff like that, or it even just encounters an invalid opcode, which should not happen, since all the opcodes in your program should be generated by the compiler and they should obviously be all valid. So in these different cases, the exception thrown will be also caught by the debugger, and you will be brought to the part in your source code where this happened. Generally speaking, debuggers can be also used to analyze programs written by other people which are only available as binaries. What you then also very much need would be a disassembler. So this is something that can transform the machine code into something that is at least remotely human readable, called assembler. So I think we will just start some very simple demonstration of how this works with the Visual Studio that I already have installed. I think the old version should be just fine while the new one is installing. No, cannot. So I need to talk a bit longer. Any questions at this point? I know I'm starting maybe from already quite a few things, but using the debugger and things like that we will then take a look in how to do it exactly. So I think it's okay if I'm maybe a bit going fast through those parts. We will look on them in detail then later on as well. Yes. So what else? Can I ask a question? Yes, of course.
Regarding the installation, because I'm programming on Mac.
Mm-hmm.
So I do have a Microsoft PC, but I usually never program there. So I would like to do all the programming on the Mac, but I'm not sure if this is gonna work, because the question I asked earlier is, I think the things you can download with the Visual Studio installer looks pretty different than the Microsoft one, and I think there's less features there. And I wanted to ask if the
I have now seen for the first time that Microsoft finally made a Mac version of Visual Studio, so I have no idea how that will look, but I would expect that you must have some ability to run it on the Mac as well. It would be strange. Ah, no, for the most part, it just needs a computer that can compile C code. So you could just use Linux with the GCC toolchain and Notepad or Nano as your text editor, and that would be fine as well. We might take a look into a few more Microsoft specific things, but it will be like individual, like one or two individual things. It will not be in any way required on a more regular basis than just to satisfy some curiosity, maybe one or two times during the lecture. Okay, so since this seems to take still quite some time, I will just start my local Visual Studio installation, which is already configured the way it should be. Let's create a new project. So when you start it, it will go through some setup stage, and then it will show this to you, and then you can select create new project, and we will just go for a command line C++. Okay, C++. This is washed. Project type console. Yes, this da. Just console application, and if you are using just standard libraries, then the source code would compile one-to-one even on a Linux machine. So for the most part, that should be fine. Although I might be lazy and just write include Windows H at the header, because that just includes almost everything that we will be needing. So here we will just go through some very initial view on. Okay, that opened on the wrong window. So let's move it here. So this is how Visual Studio looks. The most important settings you can find that under Tools and Options, and you can change somewhere the language, localization. No. So you can change somewhere the language. You can change many other things. With regard to your preferences, I would disable all the autocomplete thingies, but they are hidden quite well here around. So at this point, I would just say if you don't like all these autocomplete features, then just Google how to remove them. Okay, so and because we are lazy, we can. Let me just check how the installation is progressing. Oh, that's actually almost done. So the UI is quite simply structured. You have a main view where is your text editor, where you can edit multiple source code files at once. At the bottom you have a console view where, depending on what you are doing, different outputs will be shown. And on the right side you have a project view, where you see a directory structure, which in case of C++ is not necessarily what you have on your hard drive. So the idea is that you can add individual files, but where they really lie on your hard disk is not linked to this. So you can we can create, for example, a new directory, test, and we move the file here. And if we then look into the where that was created, then we see that the file is not in fact moved anywhere. So we see that in our test application all the files are still at the root level. This is in one way nice because it allows you to organize the files independently of their physical localization. On the other side, it might not be very intuitive. What is also worth mentioning is that if you select other types of projects, so for example C#, or I think any of the other .NET languages, the thing will in fact move files when you move them. And the reason why C++ is not doing it is that you would probably break your program if you would move one of the files without doing the required additional changes in very many other files. So in C and C++, you have two types of source files, at least the major ones. You have the source file itself, which can have either the C ending C or CPP. And then you can have this header type of file. So let's create a new one in new item. Header file. Yeah, let's call it header. And well, there it is. So what the initial intention behind header files and source files is that in the source file, when you have functions, variables, whatever, you can only use what is already defined, what is let's say known to the compiler. And in the header files, you can tell the compiler what it let the compiler know things without actually implementing them. This is done. Very nice. So let's finish this example and then we'll switch to this one. So I don't know how many of you know how much or how little about programming, but generally when you have programs, you have at some point an entry point. So this is a place where your execution starts, and in C and C++ it is the main function. Then the name of the function is defined by the standards, and actually you can have some default arguments for your main function, which will represent the command line arguments that have been passed to the application. There is also for Windows a vmain function, which is something Windows specific. So if you write a program that uses a vmain entry point instead of just main, then the program will not compile under Linux probably or under Mac. It's not really necessary to really differentiate it, so most modern frameworks don't really care for that, so you can just use a normal main function. And then what you of course would probably want in your program is to structure it more than just having everything in one function. So in the simplest way, when you write a program, you could have everything just like in your main function, but that would be awful design, and obviously for any program of non-trivial complexity, this is just not feasible. So if you want to make a very simple example, so let's say we want to define a variable. So in C++ you write the type of the variable, and then you type a name. So let's say my var1 is equals 1, 2, 3. I make a lot of variables with very simple names. So for a variable, the rules with regard to what you can use and not is it must start with a letter. It cannot start with a number. It can start with an underscore, although the standard defines things that starts with underscore, or even worse with 2 underscores, as stuff that is somehow part of the C runtime or part of the framework. So you are not supposed to make your own thing start with an underscore. And it also is not pretty to make them end with an underscore, but this is all technically legal, so it compiles just fine. You cannot use, of course, spaces. So as soon as you have a space, it's for the compiler two different expressions. You see here, it underlines it in red. So this is quite nice about Visual Studio, that it shows you programming mistakes, at least the most obvious ones, in real time. Now, I guess a lot of modern other IDEs do that as well. So if you have anything from JetBrains like WebStorm or stuff like that, pretty much everything nowadays has this functionality. But like 10 years ago, this was not a given. So let's go back to an underscore. You can use well, letters, numbers, underscore, and that probably is it anyways. You can use $sign for whatever reason. $sign does not have a special meaning, so it seems you can use that as well as a variable name. Other special characters are usually have some meaning, and you cannot use them. I would also not use $sign. That is somehow bad practice, I would say. Yeah. So you can have your program, you can have it, I don't know, let's print something to the screen. We just will need to write some include h. What this includes are I will tell later. Now we are just really researching the very basics of how a program works. So if you want to write something onto the console output, you can use the printf function. That stands for print format, and you can then write something in it, and it will print it for you. So why is it complaining? Okay, it's not included in Windows 8. I said what includes R, I will tell you later. So the thing with C++ is that it is quite advanced, and I think the best way to explain it is just to ignore a few details, show you the simple, let's say, pedagogical use case, and then explain all the details which I have not mentioned at the beginning. So you can have your program do something and then do something else. Oops. Something else. And in principle, you could, for example, if you don't want, let's make an example. So what you can, what you have in pretty any programming language is an ability to give a condition, and then depending on the condition, the program flow, the execution of the program will branch and either do one thing or do another thing. So you have, of course, many ways of doing it, but the simplest one is an if statement, which takes an equation, and if this equation is true, then it does whatever follows it. So let's take the most simple case. So we can say if variable is 1 to 3, then go to let's call it something 2. Now goto is not something you usually see in C++, but for reasons of just demonstration, we will do that. So what a goto statement is, it pretty much tells the computer go to here, to wherever the label points to. So if we would run it, we would assign the variable, we would write something on screen, then we would make the comparison, and we see that it's true. So this evaluates to true, or technically it evaluates to non-zero. So if you would have here, for example, I don't know, +1, that would be always true, except if my variable would be -1. What you could do if you want to make particularly unreadable source code, which is not advisable, you could write -1 to 3. So if this is, well, in this case it's inverted. So if it is 1 to 3, then after the after the subtraction it will be 0, and if it's 0, then whatever comes after the if will not be executed. So it then jumps to whatever is next. So in this case it would go here. But let's not do such ugly things. Yes, it is good. So let's demonstrate this quickly, and also I will demonstrate the debugger. So here you can set a breakpoint just by clicking on the sidebar. And in principle you could also set a breakpoint on an empty line, but you would then just move the breakpoint down until it finds something where it actually can set a breakpoint at. So we have our thing, and it is quite simple. When we have this project created, we just press start, and it will first compile it. So it will write some output here. It will tell where it put the window not where we want it. Although now we don't see anything, so maybe we should make this a bit smaller. One thing that is to be said about this community edition of Visual Studio, as said, it's completely free of charge, but you need after 30 days to register it with a free Microsoft account. So just create some throwaway account that you will never ever use again, or use one if you already have one. Also, you can find on the internet guides what to delete in the registry to reset this 30 days limitation an infinite amount of times. And since it's free of charge anyways, there is no reason why you would need to feed Microsoft your personal data. But anyhow, so the execution flow here and the debugger. So here at the top we have some other menus now. We have let's start with this one. Single step. This is quite nice because it just always goes one instruction further. And then we have the next one, step over. Step over means it will go to the next instruction after a function call. So if we would use this step into or single step, then we would end up in the implementation of printf, but we don't want that, so we step over, and here we can then make a single step, and we see that we did not execute this path, we jump directly to this something else line. And in principle, in a very basic way of seeing things, what we saw here is pretty much everything any CPU is doing all the time. So it evaluates equations, it makes a decision whether it should take either jump somewhere or not jump somewhere, and that's it. So there are of course a huge amount of details to that, but in a very abstract point of view, this is all it's doing. It has a pointer in memory, a register, which knows which instruction is to be executed next, and it executes the instruction and goes to the next one, and it basically just increments this pointer. Okay, there is a question in the chat. Does not offer C++. Oh, yes, you can use Xcode. Der Dingsbums da. Parallels offers a virtual machine solution for running Windows 11 for ARM, so the special ARM version on M1 chips. So since we have a Mac M1 chip user, I guess we should also take a look into how assembler looks in ARM in comparison to x64. I guess that might be interesting. And luckily I have the right hardware to demonstrate it. But anyhow, as said, so anything the CPU is pretty much doing is this: it executes the code, and sometimes you can have an instruction which in principle will check some conditions, so it will check states in registers, and depending on those states, either not do anything, so just advance the instruction counter to the next instruction, or it will set the value of the instruction counter for the next instruction to be executed onto an address where the execution should continue. And everything that then you have in higher level languages is just an abstraction of this very simple execution of one program flow. So I mean, this sample is not even really that correct, because a function call like a printf, it is already in an abstract level already something more. So technically we would really have just equations and read and write accesses to memory, plus system calls, which we should take a look into later. But as said, everything else is an abstraction from this very simple principle. So we could take a look into that, or so we can run this again and then take a look into the debugger how this looks. But first, since is the installation done for everyone, or are there people still installing Visual Studio? Okay, since no one is saying anything, I would just assume that everyone has it installed. So yeah, you can close the installer, you can start your Visual Studio 2022. Oh, it's 2022, not 2021. Even better. I somehow was under the impression the next version was 2022. 2021. So at the very first start, it needs some time. Yeah, I created a Microsoft account specially for this lecture. There is Visual Studio has a screen sharing feature, so that so that you could access my Visual Studio remotely, but that rather works not so great. So let me quickly copy the code that I created here into the virtual machine. So I like to use virtual machines for pretty much anything, so I have like dozens, and it's really advisable if you are writing some more advanced programs. So basically, it depends how complicated your setup is. I don't want to complicate things, to overcomplicate things right now, but if you have a lot of additional dependencies, additional frameworks, toolchains, etc., it's most convenient to just pack everything you need to build a given complex project into a virtual machine, and then you just use this virtual machine, you store it if you don't need it on, well, it takes a lot of storage, but it's much better than after 10 years trying to find out which tools, how did you configure it without remembering 90% of the things. Um, okay, so no, but this is not that. Did they switch to the BrightView on its own? Interesting. Open project or solution. So in your case, you would create, go to create project like I showed with the other one, and yeah, I like the bright mode, but for some reason a lot of people prefers the dark mode, so that's also up to individual preference. What you can also do is, so you can, for example, disable the menus being at the in the title bar and many of those things. So let's at least look into the most important things. So first of all, we should look into the debugger. No, that is not that. What was that? Okay, so if you go to options and type tsr, so for disassembly, you should select show disassembly if source code is not available. That is quite useful. Then you can go type symbols with debugging and symbols. You can here select that you want to download symbols from Microsoft servers, and you should specify a cache directory, otherwise that will be extremely inefficient. Let's create one. Okie dokie, and yeah, and select just symbols for all modules. Although not if you have a bad internet connection. In this case, maybe don't add symbols at all, because they are quite big. So what they are, I will tell you in a second. What else would we need? There was somewhere here the option to disable this. Disable having things in the menu, but I think how you want to configure it, how you want this to look, can be up to you. So we don't need to take too much a look into those things. These two debug show always disassembly and the symbols. That were the most important things to configure at the beginning. So if we then go back to our very first test program, oh wait, that's a very important thing to change. This the new font is hideous. I just need to check in the one I have already installed what's the right font. Continue without source code. Tools, options, consolas. I mean, obviously, that is also just something for your personal taste. Huh? But I would definitely prefer the classical Visual Studio font than the new one. The new one is hideous, in my opinion. You are free to have your own. Okay, that's the most. One more thing I really don't like is this. Like, normally I really like to have a title bar and then the menu bar beneath it, but maybe in the virtual machine, since we have a more restricted vertical space, we will just leave it as it is to compensate. Here I should be able to somehow disable the tabs. Wurscht. So let's continue with that. Let's again make a breakpoint, and as soon as it compiles again, so it needs to rebuild the project since it was moved. When you create a project and start it, you will notice that the view changes. So they are showing here different things, and also some new tabs appear here. The most important one, at least for the debugging use case, will be the call stack, where we have to do a few more changes. So when you right click here, you should select show external code, because we want to see pretty much everything that is happening and not just what happens in our own source code. We need anything else? Not really. That's wurscht. We can add debugging is already here. We should add somewhere the hex button is quite useful. So this one switches between showing numbers. So if we go to the next line, it either shows numbers as base 10 or it shows numbers as hexadecimal, which is quite useful. And here what you have, so I guess even if you are very new to programming or don't have any experience in programming, you know that when you write a program, you usually structure it in functions or subroutines, and those subroutines or functions can call other functions, and this creates basically a call tree. So you start somewhere and then you call something and it calls something else, and it my fingers calls something else again, then it returns and maybe returns again, then it does something, then it executes something else, etc. And you can see the position, your current position in the call tree in this call stack. So you see, for example, that while we started here in our main function, which kind of is the beginning of our program, in reality there were quite a few things that happened before. So first thing we can notice is that, so test.exe1 is our program, is that we actually did not start directly in, even in our program we did not start at main, but we started in some main CRT startup function, which is something that is provided by the C runtime. So the C runtime is a collection of functions and libraries which you need in order for your C++ program or C program to be able to do a lot of very basic operations that usually would take as a given. You can of course write an application such that it does not require a C runtime. It just means that you have to do much more things on your own by hand, which there are special use cases where you would want that, but in the most cases you really don't, so you just go with it. And then we also see that there is even things that have happened before the execution arrived in our program. So the way this debugger shows it, it shows the module name, then an exclamation mark, and then the function name. And what debug symbols are is which ones we enabled earlier, is a database which tells the debugger which address in memory. So as you know, a computer has memory in which it has all these things in binary representation, and there you have just addresses. So a number that represents the position in your address space. And the idea is that with a debugger you of course want to know when you are at the instruction at a given address to which function this instruction belongs, where in this function it is. And for this, these debug databases are created which contain such information. So when the compiler translates your handwritten program code into machine instructions, it writes down a, let's say, cheat sheet or a database where it says, okay, so at address 1 to 3 we have, so the instruction at address 1 to 3 belongs to line 3 of, let's say, test1 CPP, and or memory location ABC contains the variable named my variable, and stuff like that. Those informations are written into this debug files, these debug symbols, and then when the debugger debugs a binary image, it can load these informations from those files. And Microsoft is providing these informations for most parts of their operating system. So they don't provide you the source code. So, and the debug informations can be configured to contain a different granularity of information. So the debug symbols you get from Microsoft will not contain line numbers or anything, but they will usually contain at least all the function names, many variable names. What else? I think they contain file names, so that you know in which file which you don't have access to, those things at least were defined. So it is quite useful. And here, for example, we see that in the NTDLL, which is a library which is loaded into every process at start. For example, we start at the RTL user thread start function, and then we continue to another DLL, and so on. And at some point we then arrived in our own function that we have. So without the symbols, we would still see, I think, up to here, and here we would just see kernel 32 and then just a hexadecimal number representing the address where the function basically is, which called the next function. So if we would open some third-party application in Visual Studio where we don't have any debug symbols for, it would be quite painful to figure out what this application is actually doing. And realistically, normally no one would use Visual Studio for it. So there are dedicated reverse engineering tools like IDA or Githra or X46DBG, which are specialized on allowing you to analyze what applications you don't have source code for are in fact doing. So this is quite useful if you do malware analysis, or if you need to reverse engineer some communication formats or some file formats for reasons of interoperability. But realistically, so in most cases, I probably will not be reverse engineering some control software for some piece of hardware you have in the lab, because your time is also expensive, and it might be cheaper to buy something new where you have up-to-date control software. But there are use cases where you have some specialized hardware which is very old, which doesn't run on your modern operating systems. You want to write own software to control it, and then you need to, for example, figure out how the old software that only runs on Windows 98 or so communicated, so that you at least know the protocol, and for these such abilities might come in quite handy. So normally, let's continue with this debugger sample. So if you click here on a thing that you have source code for, it will bring you to the line in the source code. So you can try even for the C runtime. So here this part which happens in our exe, which we did not program, is part of this C++ runtime library, which is provided in fact as source code from Microsoft. Of course, if you would be using Linux, then it would be some GCC library provided by a few million Linux developers, or maybe at least a few 100,000. And if you would have if you are using Mechanics, Xcode, what do they use? I think they use LLVM. So also one of these open source compilers that you probably should have all the C runtime libraries for as well. And we can go up this call stack, and at some point we will reach a position where we can no longer see the source code because it's not available. It's part of Windows in this case, so the kernel32.dll. And I thought I already set that. Didn't I set that? I think I set this. I showed you where it is. Because we don't want to have this no source available window. What we want is... Okay, it's thinking. Is this, the disassembly. So I would recommend to just put it somewhere on the side. Jawohl, yeah. And let's go back to our main function. So if we go back to this function, you can see in the disassembly view what the compiler did out of our individual lines. But we will take a much more detailed look onto those things in the lectures to come. I'm here just outlining how the debugger works and how the UI of Visual Studio works. So everything that I'm telling you today about programming and how things then are maybe represented in machine code, we will take a look on all of that in detail in individual lectures. Now it's more just about understanding the UI and the workflow when you write a C++ program. So talking about the workflow, we should come back to that. So as you, for example, saw here, we already have a function call, but how does the compiler knows that this function exists, that it can be used? Sorry. So the compiler knows it because of these so-called includes. This is something that you probably in some way or another know from other languages, if you know other languages. So I think in Python it's called import, maybe. I don't know. I'm not so good in Python. In C or C Sharp, you have a lot of these imports where you include large libraries that allow you to do things. And pretty much any language that is non-trivial requires you to specify some libraries, frameworks, etc. At the beginning of your files in order to know what functions, what objects will then be at your disposal. And this include statement with this header files in case of C and C++ is quite interesting, because what basically this include statement does is it takes the content of the file, in this case Windows H, and it pastes it exactly here. So let's demonstrate that. I can make a new file. I can make a and you can include pretty much any file. So the convention, of course, is you include header files with the H ending, and that's it. But in principle, you can just create any file you want. Call it source. Let's call it source inc for include. And then just copy a portion of our code into that file, and then we here just write include. Sorry, hash include. What was the name? Source inc, just inc, and it is not complaining, and it will in fact work. So if we run this, it will just run as it ran before. We will be able to step through it. Let's do the other step function step by step. Then we end up in the other source file. So with all other languages where you have import or any other sort of adding libraries and frameworks to your files, this does not work like this. It's really just a information that look there for this and so on. But in C, it's really that brute force way implemented. Another thing that is also probably interesting with regard to this demonstration. So another thing important about the include statement is that you saw me using it here with normal Anführungszeichen, what's the English? Brackets? Not brackets. Quotation marks. With quotation marks, while yes?
Is it possible to zoom in your code to make it a little bit bigger? Because if I split up my screen and try to write,
Yeah, like this.
yeah, that's better, thank you.
Okay. Yeah, sure, why not? Where were we? Yes. So you can use an include statement with the quotation marks or with this smaller than and greater than signs. And the difference is this quotation marks you use if you are including files from your own project. So files that you have here in your project directory or in a subdirectory of a project directory, etc. The pointy brackets you are using if you are including files which belongs to frameworks or libraries which are installed in your or with your IDE. So ones that are not part of your project, but something that anyone, for example, could expect to find if they install Visual Studio. Or if you are using more advanced frameworks, if you install Qt, for example, then you would have all the Qt includes integrated into your Visual Studio or into whatever other development environment you are using, and there you would also use this pointy brackets. If I remember correctly, it does not really makes a difference. So this is this autocomplete, which I really don't like. If we do it like this, as far as I remember, it will also accept it. The only downside might be, we are in this not quite consistent state right now. The only difference that it really makes is that your program may take longer to compile, because it will first look for the files. Yeah, it also compiled. It would with this normal quotation marks, it will first look for the files locally, while if you use the other ones, it will first look for the files in all the include directories which are configured by default. And you can change those include directories and many other directories if you go to the project properties. So on this page, you see there is a lot of things to configure, but for example, Visual C++ directories, and here you can add additional include directories, and as well as library directories and a few others which you might need. So unfortunately, we don't see what everything is here included. You have just these placeholders for a whole list of standard include paths that are provided by Visual Studio. But if you would, for example, use some own framework which does not integrate with Visual Studio, you could add the include paths here, and then still use this pointy brackets with reasonable performance in your own program. Although I guess with the speed of modern computers, that really will not make a difference at all. But like in the good old days in the last millennium, things were much slower, so such small, nowadays almost meaningless optimizations actually were not completely pointless. Now to the next thing. You might be interested in how such a header file looks inside, so we can actually take just a look into one of them. If you select anything in your code and then press F12, or you press Shift and then click on it, then it will bring you to the definition. And we see, for example, that this printf is defined in this standard IOH. We also see the path where it is, where the file actually is, if we move the mouse over the tab. And you see that it is just a function definition, so it tells you what the function is, but it does not really tell you anything else. So you don't have the body of the function. And this is the first thing we will now take a look on, how you define anything in C++. So let's say we make a very simple test function. Let's call it my test. And first of all, we need to give it a return type. So if a function and a subroutine in some languages are declared quite differently. So I think, what was it, Fortran has, or was it Pascal? One of the older languages, doesn't matter. You really write explicitly whether it's a function or whether it's a subroutine. And the semantic difference between a function and a subroutine is that a function returns a value, and it can be used in a mathematical equation, while a subroutine does something, but it does not return a value which would be usable in any sort of expressions. In C or C++, this is quite mostly the same thing. It just differs in the return type. So you can either have, for example, an integer, it will be an integer number as a return type, or if you don't want to return anything, just write void, which is a non-type. It's like the void keyword is a placeholder for something that's undefined, and if it's a return value, then something that is not there, simply speaking. But let's go with int. Then we need two brackets, and then we can write some arguments which we might want for the function. So let's say int a, int b. So we define arguments the same way we define variables, just by writing the type and then writing what they the name. So the name can be, as said, anything that starts with a letter and has numbers and underscores, and that should, and hopefully no other symbols. And then we have curly brackets, and then the function can do something. So let's say that's obviously super trivial, but a nice example. So the return keyword has two functions. First of all, it terminates the execution of a function, and second of all, if it's followed by something, then the result of the following operation will be returned as a value. So if this would be void, then the compiler would say that we cannot return anything, and it should be just a return without arguments. And if you would want to use this function for something, we already had, oh, that is okay. Then the compiler here will complain, at least it should complain if we try to compile it, that it doesn't know what my test is. So even if it is not underscoring it here, when really compiling, it says that it doesn't know what this function is. And the reason is that, as I said earlier, C and C++ only know everything that came before it. So it's on a very basic principle, a very simple approach to compiling. So you might have other languages where it doesn't matter where you define the functions, because they will be going through the file multiple times and then first make a list of all the global variables, a list of all the functions, etc. But C++ is, for I guess reasons of performance many ages ago, designed such that it really just tries to go once through all the files and not have to repeat itself. So one thing that you could of course do is just put the function here before your main, but this would of course bring quite significant limitations. If you would always need to keep a certain order, then you could not be very flexible with recursions and stuff like that. So what you can do in C and C++, and what you should do, and what is basically the content of most of the header files, is you just write the function header, or the function prototype, without the function body. So you just terminate with a semicolon. In C and C++, almost any expression is to be terminated with a semicolon, as you see here and here and here and there and here and so on. Not here. Labels have a double point. And now the compiler will, going through the files, there will be a file called mytest, and at this point it does not even care where this mytest is. It just cares that it is. So we could create a new source file. Let's call it test cpp, and we can move our test function into test cpp, and it will still be just fine. It will still run. I mean, we're not doing anything with the return value, but we see that it compiles. And now what you see also is that when you go again on build, that it compiles every file for its own, and then in the last step it links everything together. So every file, where do we go here? It gets compiled into an object file. So we have test object and we have test1 object. Okay, the other file is called test1. And they, during the linking, are put together with a lot of libraries that are provided by the development environment, in this case by Visual Studio. So when we go on inputs, we see here a huge list of libraries which by default are already added to every project that you create. So you could of course disable those and then just add hand-picked libraries. But yeah,
What did you put in the file to call the function instead of defining it beforehand?
nothing. You have to define it beforehand.
And that's it. I thought you said something about putting something in a file which I missed. But if that's all you have to do, then
Yeah, well, what you normally do is you create a header file, and you don't define like everything every time over and over and over again. When you want to use it, you just define a header file. Let's call it test header. There you put your what was it? There you put your definition, and then here in your file you just include.
yeah, that's exactly what I was asking. I understand. That's what I mean.
Yes.
See what you
So you just include your test h, and the nice thing is then that your test h, it can contain hundreds of functions. I mean, there are some limitations. I run once. I think if you have more than 10,000, was it 5,000 members in a class, there are some limitations, but that's not usually things that people are supposed to run into. So for all practical purposes, you can have almost as many include definitions in your headers as you want, or members in your class, etc. And now if you would have a lot of files which all needs to use our test function, you would just let's add at least a few empty lines here so it looks nicer. Then you would just add this include test into each of them, and you would not need to care like if it would be something more complex. So if it's really just one function, then maybe just put the definition everywhere. But normally you would have something more complex, or a huge collection of functions, for example. And in those cases, you would want to put all those things into these header files. And one moment, please. Okay, so where was I? Yes. I really had to be the fun for one. So let's just start again. So you can yes. Well, we write it. We write the type int such that it is int. It could be something else. Yes, exactly. But we'll take a look into functions in more detail later. Anyways, this is like a rough overview. So yes, normally in your header files you would have much more complex things. So talking about complex things, normal C is quite trivial because it knows only functions, variables, and structures. And and a structure, let's quickly demonstrate it. A structure is pretty much just a collection of, let's say, a collection of variables. But really, for the computer, the structure is just a piece of memory, and the fact that it's split into variables is something that is useful for us when we program, but the computer internally does not have this separation at all. It's just one larger block of memory. And you cannot even have any other members than variables in C. So if you want to have anything more complex, like classes, which can have member functions, and we will take a look on that later, then you need C++, which is, let's say, comparatively much more advanced, but it still follows the same design principles of normal C. And we will take a look on a low level onto how C++ implements all the functionality that you get, that is, let's say, quite impressive even, on a close level. So you can in principle write a pure C program and from it still interact with a library or something that uses C++ classes. It just means that you need to do much more things by hand. We will take a look into this in one of the later lectures as well. But yeah, the important things are that generally such definitions, you would pack all of this into these header files, and what you might run into as well is if you have a header file. So a header file can include another header file recursively. So we could we have this header H here, so we could in this header include include header, and now we might think that we might have a problem if we include the header here, because then it would kind of be included twice. But in fact, there are mechanisms to prevent this. So you have here this preprocessor statement, which just says pragma once, which tells the compiler that this header file should not be, basically that it should only be included once. But this already is in a way a C++ feature. So if we would want to by hand prevent recursive inclusion, we can in fact do that. So let's comment this out. And this preprocessor is something that is available in C and C++, and in a way it's like a very trivial programming language within another programming language, because what it pretty much does is there is like a dedicated preprocessor step, and then these instructions are executed, and what they do is like the include instruction, for example. It tells, okay, take another file, the content of it, and paste it here. And then you have other instructions. So we could have, for example, an if statement, so a conditional instruction, if or if. So the opposite. So you can have if def, which means if defined, or you can have if and def, if not defined, and then we just write header h. We just write a name we invent. The standard is that you for this application just take the name of the file, and instead of the dot you make an underscore, and then if it's not defined, then you define it, and then at some point you made end if. And the idea is, if we take this and put it into all of our, okay, we need of course to change this here to test. file. So now when the preprocessor starts in our C++ file, so this is another important thing about C and C++, that only C and C++ files actually get compiled. A header file is just a text file. It will not be converted into anything unless it is included, and then it will be processed and converted as a part of what has been done to the C++ or C file. So in this example, when we start here, we say include header. So actually we could do an example. Okay, let's just reuse this file. What we can do is we can make a side view. So let's say that we add a, oops, that was not intended. So let's say that we add a precompiler. So we see the file. We ignore this for the moment being, because that's too complex, and we see include header. So we go to header, and really as simple as that, we just do it. Then we go to test. But when we go to test, we see there is again include header, and in this case we then take this and paste this here again. But now if we start, if we do the next iteration of the preprocessor step, so we will see, okay, if not defined, then define until the end. If then we said if not defined, define, and then we see if not defined, but it is already defined. So this condition is not longer true. So then we see, okay, where's the end if? Here it is. So let's take the text block and remove it again. It's a bit trivial, but in pretty much all detail, this is what preprocessor is doing. It is just editing your code, and when it's done with all the preprocessor steps, so of course the last step will be to remove everything that is not C code. And then it will just compile it, feed the compiler, the actual internal compiler with it. Some older compilers, in fact, had options where you could get these files as an intermediate output from your toolchain, but I don't think you can do that with Visual Studio anymore. And it probably would not be very useful anyway, since if you do a thing like include Windows H, I mean, maybe Windows H is not so big, but it includes things that you would end up with 10,000 lines of or maybe at least hundreds of lines of includes. So this functionality is not longer present in modern toolchains, but it's, I think, quite nice to have this understanding, because there might be use cases where it helps you to structure your source code, like really by then just having a include and then including a C file from somewhere, which well, you can do it. So C++ is quite, or C in C++ is quite tolerant with regard to what the people that write the programs are doing, so we can do many not necessarily super nice things, but usually you should try to stick to standards which will make your code readable. So another interesting thing is that line breaks don't matter. We can write the whole program as one line, and spaces mostly also don't matter. Okay, some spaces matter, like when you have a type and then you have the variable name, but all the other spaces don't. I mean, Visual Studio has this function that nowadays auto format, so if you press the semicolon, it will format the line for you automatically, but in principle really could be really, I mean, you should not do such things normally when you are programming, but it's good to know and understand that such things can be done. And okay, wait, go to, okay, there we need a space. Yeah, and this will still do the same thing. It will write what was it, something and something too on the screen. So you have a lot of opportunities to save lines if you want to, and sometimes it even makes for more readable code if you do such things. But usually, if you have a larger complexity, you should not do that. Okay, so that much to the very basic structure of C and C++. And the next thing we will do is to start to taking a detailed look on everything. I think more of this general point of view we will not need. Yeah, I think that, I mean, the other things we will take a look on other things as we encounter them during the more detailed look into everything. Maybe one more note. Since the process of building a binary in C and in C++ is a two-step process, so that you have first the compilation and then the linkage, obviously you can run into errors during both of these steps. So the first sort of error, let's just screw something up, my test 1, is very easy to fix because it tells you what's wrong and it tells you where it's wrong. So you see, it tells you exactly here, my test is not found, and if you double click on it, it brings you to this line, it underscores it, and it shows a marker, so it really tells you what's wrong. The other type of bugs is much less pleasant. These are issues which happen when you link something. So let's say we rename this function to test2. We have changed here back to the test, and now we run the compiler. You would expect it will be the same error, but no, it will not. It will be a completely different one. You see, first of all, the compilation of the source files went just fine, because when the file is compiled, the thing says, okay, we need a my test file, and it sees in this included test file, okay, this will be my test, it will be somewhere. It expects it at this point, that either it will be found further down in this file, in which case it will be created and compiled to position independent intermediate representation, or what in our case happens is it's in another file, and here it will be compiled again to a position independent intermediate representation, and then during the linking step those things will be connected together. And if this name of course is wrong, then this linking step fails. So all the files compile for themselves individually just fine, but then we get some linking error, and these are quite annoying to fix, because they usually don't tell you where the issue is. They say what the issue is. They say in this case that a function called myTest is referenced, but it's nowhere to be found. And if we take a look to main, this, for example, printf, we don't have anywhere. Printf will be in one of the library files. Which one? Let me think. I think it will be in kernel lib32. But it doesn't matter at this point. The thing that matters is that the function must be either in a library file or in one of these object files, and the problem is that it doesn't really know where it should be, because it doesn't know your intention. It doesn't know should my test be from a library, should it be from which library. It just knows you used it and it's not there, and unfortunately it's not even nice enough that it would allow you to double click on it and bring you to the line. So then you need really to check, okay, it's defined in, it really tells you where it's defined. Yeah, it's referenced in function main, so you look into your function main, and then you just have to look for this text, and then you see how, okay, it's here, and then you can have to think about what the error might be. So why isn't it working? Of course, the same thing would apply to a global variable. So if you would have a global variable that is defined as being there but isn't there in the end, then we would get the same sort of error. And you can in fact run into other much more difficult to fix linking errors if you are using some libraries from third parties or some strangely configured projects. So normally if you just write your own program, what we will be doing most of the time, you should not run into any linking error other than what I just demonstrated here, that you accidentally had a typo in your function's body's name, while you have it defined differently. but if you are, as said, using some special libraries or libraries that other people have compiled with different presets, you might run into very esoteric linking errors, which are then really, really painful to fix. Just to demonstrate, maybe not demonstrate, just to tell you, one place where you can look for fixes is general code generation. And all the settings here are usually something that to be very careful about, especially the runtime libraries. So if you have a different, so if you would have two projects which are linked together, so like one is creating a library, and then the other one is including this custom library, and they are configured here differently, then this will not work. If you are using dynamically loaded libraries, so DLLs, that's a completely different story. These are much more robust with regard to those things, because such a DLL is already linked and is just exporting a defined interface somewhere. But the lib files as such, so if we would compile a library and make from some project, you could open it in fact with, for example, 7-zip, and inside you would just have a directory with a lot of object files. So a static library pretty much really is just a collection of object files, as normally during compiling any C++ project is generated from every source file individually. Yeah, so that's that. Let's then. So the lecture is written to be free till 5:30, but we only have 3 lecture hours. So technically we should have a 15-minute break somewhere. And I think now would be, since we now like took a look on the compiler and had some basics, we should make maybe now this 15 minutes break, and then we will start with the first in-depth view on how those things work. I think that sounds like a plan. So let's continue, since we already are a bit over time, at 4:40, so in 11 minutes from now. So it's not quite 15 minutes, but I think that is fine enough. I will then be back at that time, unless you have any questions that you want to ask me right now. So you can also use this 10 minutes for you asking questions if you already have any additional ones, and the others, if they don't have any questions, can I don't know, run in a circle to stretch their legs or something like that. Okay, no questions. Then I'll turn off my mic and my video for the 10 minutes and see you in 10 minutes. So I'm 1 minute early. Did anyone came up with any questions in the meantime?
I have one more question
Yes?
regarding the usage of the IDE.
Mm-hmm.
Because I'm having issues doing some on the Microsoft PC. I try again, but is it an option to use something else? Like someone mentioned Xcode, which seems to be easy to install, but it's probably worse. Do you have any recommendations in this part using a virtual machine?
Uh, hmm. Um, Depends. I mean, I would, for my use case, always just go with a virtual machine. But I think since there should not be, well, it depends on what we'll be doing in detail, because in turn depends on what you express interest in. So there are like some selected basics for the lecture, and there are things where, like, if you are interested in this, we can make an in-depth dive on that. So, but within the normal plan, what is envisioned, you will not need most of the advanced features of Visual Studio. You only need something that you can feed a standard CPP file in, that will make you a binary out of that and run that with some debugging capabilities. And Xcode should be good enough for that. Um, what is quite nice, but it's, well, some effort to install, I'm not sure how easy that works on Mac, would be a Qt Creator. It's a IDE especially for the Qt framework. On Windows, it's available for Windows, Mac, and Linux. But on Windows, you have a plugin for Visual Studio, and it's just better to use Visual Studio, at least in my opinion. But from what I remember of it, so I used it a lot in Linux, and I used it on some Mac virtual machines a decade ago or so. That it had all the most useful features. It's much more cumbersome than Visual Studio, but at least I think it has this disassembly view and all the debugger capabilities. So that would be worth looking into. Yeah, but I think Xcode should be fine, at least for most things. Okay, so since we are already 2 minutes over at the break, so I think everyone is back here again. So we will create a new project. New project. Again, a console application. Let's small enough. Let's call it variables. So the first very basic thing we will take a in-depth look into. Huh? Oh, I pressed on back accidentally. Will be variables and how they are, how you can use them in C and later in C++. Because there are quite many limitations with regard to variables in comparison to what one might expect if one is already experienced with some more high-level language, like, let's say, Java or a script or Basic or Python. Python is very very popular. So the typical expectations for a programming language and for variables is that those variables can be quite a lot of many things. But in fact, the CPU on a hardware level can really only handle the most simple so-called machine types of of data, and everything that goes beyond those is only implemented by some features of your frameworks of your programming language. In case of C and C++, it is particularly interesting because most languages, like let's say JavaScript or this Python, they give you some abilities to create your own variables and types, but there are quite many things which are provided, which are high level, which are complex, and are already provided by the framework that you always have at your disposal, and that you can use. And in C++, you don't have this high-level frameworks which would come from outside your programming language. You have a lot of high-level frameworks, but you pretty much get them implemented in C++ themselves or in C. So you can, if you have the source code, of course, look back into how those things are implemented to the very basics, where you only operate with machine type, with things that the CPU as such can understand. A perfect example of a variable type that anyone would assume as there must be such a thing and it's very useful, which doesn't exist for what a computer as such is concerned, or a CPU as such is concerned, is a simple string of text. So for a string of text is something that you would expect in your program to need it everywhere. You want to print something on the screen, you need a string of text. You want to do some text processing, you need a string of text. The CPU does not have a concept of a string of text. The CPU has only a concept of a very few data types, which in the case of a 64-bit CPU is a single character. In C, the keyword for character is just char, so let's call it my char. This is 1 byte. Let's give it a start value, and so it's the comments. Oops, my virtual machine lost focus. So it's 1 byte, one byte. It can have a value from -128 up to 127. Why the negative is bigger than the positive, I will explain later. The next type that the CPU can handle natively without any, like in one instruction without any things, is a short, which is simply 2 bytes. And this pattern kind of repeats in powers of 2 until we reach the bitness limit of our architecture. So this can be -3002.768. I'm not writing those things out of memory. I have a cheat sheet. Because I mean, I would know these values by heart in hex, but I don't know them in base 10 representation by heart. So as said, the next one is a either int, or it can also be called long. So there are a few types which are let's say context dependent. So the idea is that the integer always represents the length, the largest type, no, maybe not the largest, but the default type, the default length, which normally is also the largest length on any given architecture. So if you would have some Arduino microcontroller, for example, those are 8-bit CPUs. But I think the int there even is not quite as defined, but it's already a 16-bit value, because like just a character would be for most applications too little. So int normally just takes the place of what's the most reasonable integer value to use on a given architecture. Although, as said, it was intended at some point to be like the native length, which is also the maximum length. But ignoring int, something that is eindeutig, unique. What's that word for in English for eindeutig? Wurscht. Something that has a fixed meaning and is always the same thing is a long, because these are defined as 32-bit. And these are 4 bytes in length, and they can be quite big. So, yeah. Sure. Okay, so now I'm too lazy to type, so I have already my cheat sheet prepared, so I don't need to type too much. Yes, and what you also have is you have, let's say, aliases. So for you can write those things sometimes with other expressions. So in C you have a few ways of making alias names for your types. One is just using a my type int. So you just write a name. Oh, sorry, was it this way? You write a type, then you write how you want to call it, and then you can just refer it under this thing. So you can define pretty much any type this way, or you can use the preprocessor define. And what the preprocessor does is when it finds this, it will replace it with that wherever in your code you have this. But like really, like we saw it earlier with the include statement, it really just goes with a brute force copy and paste approach, while the type def is an actual type definition. But the thing is, with regard to the built-in types, so things that you can use or that you can write that don't rely on those methods of introducing custom types, is these other names that you can use. So it is you can also write short int instead of just writing int. I don't know why it is acceptable, because it's kind of redundant, but if you write short int, it's it tells the compiler the exact same thing. I think that the idea simply is that if you really want to make things eindeutig. What's eindeutig in English? Ich stehe auf der Leitung. Does anyone know what's eindeutig in English? Okay, I have to Google it. No, clear is klar. Unambiguous. Now we know. Okay, so that to make it unambiguous, the idea is that because you can use this long and short prefixes also for other types than int. So the idea actually is that you are supposed to tell it what it would be, and just writing short is like a shorthand, or just writing long is a shorthand. So you can so this is basically just an alias for either for long int or just int. Then of course, if we have a 64-bit CPU, we have even larger 8 bytes types, which don't have a nice name anymore. So the base type is just int64 for whatever reason with 2 underscores. This 8 bytes, and this is a really huge number from this up to this. And you can also write long instead of writing int64, which is I mean you probably can also write long int, I think. Yeah, of course you can. But using int64 is more, it's just nicer to write because it's shorter. And often when writing programs, it is nice to do whatever you can to save on typing. Yeah. And the next thing that the CPU can natively work with is a alternative representation of these numbers. So these ones can be positive and negative, and the same amount of memory can be also used by a exclusively positive number, so-called an unsigned number. And just to copy those from my little cheat sheet, these are those. The way you generate them is quite trivial. You are just taking the unsigned keyword and putting it in front of whatever type you want, of whatever integer type you want to be unsigned. And in fact, there is also the type signed, which you could put here to have it explicitly signed, but they are all by default signed, so there is quite some redundancy in how those things here are implemented. And these values, so it has the exact same number of values, but the values are mapped to a range from 0 to 255 or 0 to 56,535, 4 billion, what was it, 18 exa, doesn't matter. A very large number. And these basic machine types, you can also of course have multiple of those, so you can have an array of characters or an array of shorts or an array of longs. And to go back to our example of a string, and that we use it everywhere, normally a string will be an array of either characters, shorts or longs, depending on your platform. So on Windows, so there are two things of strings. There are so-called ANSI strings, which are just a string with, with characters, which contain the standard US alphabet and a lot of special cases. I mean, like Sonderzeichen, special characters, not special cases, special characters, and that's pretty much it. And they are on any platform represented pretty much the same way. And then you have so-called wide strings. The idea about wide strings is to provide Unicode support, so that you can use languages with letters that don't are represented in the standard American alphabet. So like if you have, although I think within, so the standard ANSI range of values is only 0 to 127, and there are some of the like in the upper memory range. So if you go with this representation, where you have a few at least of other language characters like umlauts and a few other ones, but at least as quick as you go to Chinese or Cyrillic or anything that's not completely mainstream Latin alphabet, you will need these wide characters and Unicode support. And in fact, the way Unicode works is that you nowadays even smileys and all the other thingies have a Unicode representation. So this requires, of course, that every character, let's say, can have much more values. And on Windows, this is represented with a short. So you can have 65,000 characters. Many of them are then some Asian words, since their language is based on one character basically being a whole word. But since 65,000 apparently was not enough, you can have Unicode characters which are made up out of two short UTF-16 characters. And on Linux, I don't know about Mac, I guess it will be like in Linux, these wide strings are actually implemented using arrays of longs. So there you don't need to break anything up into two parts. You just, well, 4 billion entries is enough. In the most use cases at least. And how the strings then really are handled, we will take a look on later, but it's just important to know at the beginning that the CPU as such does not know what a string is, and that it is just a, let's say, artificial construct made out of many instances of a standard machine type. The next thing that probably is interesting, especially for physicists, are floating point numbers. Because, well, integers are nice, but if you want to calculate some function or something, you probably want some commas. And there are in fact two types which are natively supported on any modern CPU. Float. And if you write it like this. So you just write comma 0 even if it's just 0, and then F to indicate that it's a float. And this is a for where's my mouse? 4-byte. I have pressed some. Okay, it's a 4-byte variable, 4-byte type, and it can have quite a large range of values. So it's plus minus, well, it's 0 up to this, and with an exponent it can be up to this size. So it is quite a large range of variables that you can of values that can represent, and of course it has a limited precision. So you cannot, like you have a large range, but you cannot really address every single number in that range, but rather because the idea is you have a certain amount of as a part of the value, let's say that is just a value, then you have an information to which exponent this is, and then of course you have an okay precision within around the value range at the magnitude of the value that you are representing, but you don't have arbitrary precision. So this might not necessarily be ideal for actually it's pretty shitty for most scientific calculations, unless you are doing some neural networks, then that is even too much. So like modern neural network accelerator hardware works with floats that are only 2 bytes because it doesn't matter. It's so unprecise that it really doesn't matter. But for anything reasonable that you do knowing what you are doing, 4 bytes is like the absolute minimum, and hence we have another type which is called a double, and double just stands for double precision. Which is written very similarly, just without the F, and this is a 8 bytes type. And the interesting thing is that these doubles, they are available on a lot of architectures which natively can normally not handle 8 bytes, which is 64-bit. You may know or remember from the good old days that, like in the year 2000 and before, all computers that were sold on the for the end user market just had 32 bits, were 32-bit CPUs, and only some were around 2000. What was it, 4 or so? Yeah, 3, 4, 5, somewhere around this time. AMD introduced the 64-bit CPU architecture, which then was widely adopted. There were, in fact, since 2000 or even before, some 64-bit architectures from Intel, the Itanium line of CPUs, but it just never found widespread adoption. So in those systems, you could only have those 3 types and those 3. But you for floating points, you already had still your 64-bit double type, and some internal representations even could handle higher precisions, but it also was not widely used since for compatibility reasons people just everything programmed with this standard precisions. Yeah. If you want to see the limitations of all the different data types, so like the value ranges, there is a website where all they are listed. So if you look here, then you will see a list of all the different data types that are machine types in C, and which value ranges they really can provide. So I mean most things are already here anyways. Okay, so are there any questions at this point about machine types and variables? Okay, so then let's quickly take a look on the binary representation of these different types. So as you all know, computers works with zeros and ones, and internally every byte is made up of 8 bits, so 1 like 8 bits. Oops. And interestingly enough, there is like a in between size, which is a nibble, and every byte are 2 nibbles. A nibble is of course so 1 byte is 2 nibbles, and 2 nibbles are 8 bits, or rather 2 times 4. So a nibble is 4 bits, and the reason why this is so we will see later here further down. So we have here the different representations of a few selected values. So you see here 0 is of course all zeros, 1 is binary, the first 1 is 1, of course in the hexadecimal representation it's also 1, and then if we go to 2, then you have then you set the higher bit, then you clear the before bit, and so on. And so basically you can count on your fingers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and I ran out of fingers, which is correct because you can only count from 0 to 31 on your fingers, unless you use the other hand, then you have 10-bit resolution. I don't think anyone could count on their toes, because that's already difficult enough, since humans don't have full control over those 3 fingers. They are linked together, so moving them independently is a bit complicated. But anyhow, the idea with this nibbles is that one hexadecimal number is 1 nibble. So if you have a char or a byte, and you represent it with 2 hexadecimal numbers, then one of them is a nibble and the other one is also a nibble. And of course, if we have larger numbers, then like you see here, we just make them longer as required. And now we take a look on the representation of negative values. So here, for example, we see that -1 is all the bits are set, and 2 then is the last bit is not set, and so it's basically like an inverse of the positive values, a full inverse, just that the mapping is shifted by 1. And this is also the reason why here in this representation the negative values are always 1 value larger, because they have the whole value range for themselves, while the positive values have to accommodate for the 0 as well. And the reason this is implemented such is that it allows you quite easily to implement mathematical operations like the basic ones, addition, subtraction, etc. in hardware. While if you would want some sort of symmetry, like to have like a -0 and then -1, 2, etc., this would not be that easy to then compute. And for the very early computers, it was of course very important to be able to create all those mathematical operation units with as little transistors or even vacuum tubes, if anyone here knows what a vacuum tube still is, or what was back then. So they just picked a representation which might not be perfectly elegant, but which is very, very, very simple and works quite nicely. Another nice thing is that if you have some unsigned values and you want to assign the highest value possible, you just always write is equals -1, and the compiler then really just fills in however many ones you need for this particular size. So it's also from the programming point of view a nice thing, because you don't need to know which type you have. I mean, you could also go with the largest type and then cast it down, but typecast is something for shortly later. The next thing that is important to know when programming is how to enter those variables. So we already have like shown you that you can just write a decimal value, you can write a hexadecimal value, and one thing to notice that a hexadecimal value always starts with 0x, and unfortunately C++ is here a bit let's say problematic, because it also supports a so-called octal representation. So where you have values only from 0 to 8, which is the analogon of just 3 bits. So we have here again the 3 ways how we can write something. So all of these variables are assigned the decimal value 1 to 3. So to assign decimal, we just write decimal. We can also write negative values. That's perfectly fine. For binary, we just write 0b, and then you write the individual bits. For hexadecimal, 0x, and then your nibbles. And for octal, you just start with 0, 1, with 0, and then just without any special character, just write your number. And in my experience, it's sometimes that if you want to format things nicely, that you might be tempted to start some decimal value with a 0 to have all your values the same length. But if you do that, then you are switching to octal, and that is shit. And the compiler will only warn you if you use here a value larger than 8. So basically, if you just use Wait, is it true? No, larger than 7, because 0 is one of the numbers. It can be 0 until 7. Um, okay, so characters we already said. So if you want to write a character, like as a ASCII character, so enter the letter A or a bracket or something, then you write it in this single quotation marks. And then internally, the thing, I think there was a reason why I chose this, because this is that? No, that's not 1, 2, 3. What number? No, it is 1, 2, 3. It is fine. Then this is wrong. 120. That should be B. So 1, 2, 3 is pretty much just this letter. So the standard, the American standard alphabet contains a lot of special characters, which most of them are used in different, in programming languages. They are used in text-based data formats, etc. So we have here again the same character in the different representations. And lastly, we also here have again a table how the different values look if you're just setting 1 bit. So it's quite nice if you want to set values that you remember for the hexadecimal representation. Just go 0 to 8 for the first 4 bits, and then again 0 to 8 for the next bits. In Octal, no one uses Octal. That is just purely historical reasons why this is even supported, and in my opinion they should have removed that long ago, because people might write things like this and not realize that this is not a base 10 number anymore, just because it starts with a 0. And of course then the decimal representation. Yeah. So one thing that you can do with your variables, which the CPU doesn't care about in the least, but the compiler does, is to define them as constant. So if you write something like this, const, then the type, and then the variable name, and then a value, then this value will be assigned to the variable, and you are not supposed to be able to change the value. Of course, the computer, the hardware, the processor does not have any means to protect memory from being written at this level of granularity. It has great many means to implement various types of memory protection, which we'll be talking about later, but they all are at a granularity of about at least 4 kilobyte. So you can set like this memory is read-only, this memory is executable, or this memory is not executable, with a granularity of 4 kilobyte blocks, which are called pages. Technically, you can have architectures, or even within the normal Intel architecture, you can configure the CPU in theory to use a different page size, but that's something that the operating system kernel would have to do because it is managing all the pages, and that's just not something that is done. So I guess if you build some own custom Linux kernel, then you can use different page sizes, but except for this fringe case, you always are stuck with a 4K page size. So this const variable is only meaningful for the compiler itself. So the compiler itself will see, okay, this is a const, and if I try to assign it 4, 5, 6, and then I try to run to compile the program, it will throw an error. It will just outright decline to compile the file with the error that I cannot assign a constant value. And we will come to that. This can be faked around, let's say. I mean, that was planned for later, but actually it makes more sense to say it now. So what you of course might want to do is you might want to, so we have this to my short and my char, and for some reason we might maybe want to assign to my short the content of something that has a different bitness of my char, for example. And normally the compiler is perfectly fine doing so, and also doing the opposite. If you make char is like short, it will also do it, although in the later case it should at least throw a warning, because if you do this, as we see these representations here, like assigning this to that, you have enough room. You just assign the two lower nibbles, and you clear the top, whatever the top is. So you can assign also a character to a 64-bit number, it will just make all of those zeros. And that is quite nice. The other way around, if you assign something here bigger to something smaller, it will also do it, but it will just take the lower 2 bytes, two nibbles, sorry, or the lower 2 bytes if you are assigning something that has 4 bytes to something that has 2 bytes, and just completely drop whatever is above it. And because this is a loss of data, so for example, let's say you have a loop and you have a counter, and let's say your counter is at some point only 8-bit wide, and you want to count to 300. Then you will be counting, and your number will never ever reach 300 because it will always be at some point truncated. So normally the compilers should throw warnings. Let's see if that's the case. No, it's not. Yes, here. So warning: conversion from short to char, possible loss of data, and this is important. That is also a good source of bugs which might be quite difficult to find because they may only happen in certain fringe cases. So it is good to take care about it. And one thing you can do is, of course, you can, if you want the warning to be gone, there are two things. First of all, you could just disable warnings, which I absolutely not recommend. You can disable a warning temporarily using a pragma directive, which we will not take a clear look into. And the typical thing that you would do in such a case is you somehow need a way to tell the compiler, and at this point, I know what I'm doing, it is fine. And this usually is a typecast, so you just write that this will be a char. So you write a type in normal round brackets, and this tells the compiler that convert this to that, and I know what I'm doing, don't warn me if there is data loss here. So other assignments which will cause warnings is, for example, if you are assigning a unsigned to a signed number or vice versa. I think the only exception is if you are assigning -1 to an unsigned number, because they know that people just always do that if they just want to assign the largest value. So there it explicitly does not complain. But I think with other ones, depending on the settings, it will. And what you can do with this typecast is you can convert from various types to others. And in case of this conversion, this is quite simple because it just, as I said, it's just copying a few bytes. But what if we would want to convert something else? Let's say we want to convert, I don't know, let's say this here, to a double. The representation of a floating point number is completely different than the representation of a integer in memory. Therefore, there are special instructions which allow the CPU to do the conversion for you. And in this case, that probably will not throw any warnings because we have no data loss. Yeah, and we can see in assembler, so what the computer generated here is just a move operation, which then copies the content from one address into a register, and then it moves it back. What are registers? We will take a look probably to next week, since we are almost running out of time already. But it just uses a different instruction and different registers to convert, in this case, if we have a double assignment. But what I actually wanted to show you with regard to this const is that we can, in principle, in theory, that goes a bit far, but I will just demonstrate. We can take a pointer, so we can take the address of this thing. I should not be demonstrating. Gosh. Tell it that it's just a, what was it internally? It's an int. Oops. Then take the reference on it, and this equals 16. We can, using pointers, which I will describe in the next lecture, or maybe in the lecture after that. We'll see how fast we progress. You can force the compiler to allow you to write to a constant variable, and this will work just fine, doing this sort of typecasting. it will, when I say it will work just fine, I mean it will compile and it will run. It does not mean that the program will behave as expected, because what we will also take a look into during later lectures, this arrays of things. Like I said, strings, for example, are just arrays of characters. You can define an array, and if you are defining an array in a program, in a function, then you need to tell the compiler how big this array has to be. And you can either just write the number down there. So let's do that as a demo for things to come. So let's make it a int my array 1 2 3, and this is just an array which has one. Okay, that's maybe too many. Let's give it 3 elements. 3 elements, and we can fill the elements 1 1 2 2 3 3. So just like for a single machine type, you just write whatever value you want. If we have an array, you can write in curly brackets and then the values. And in principle, we could have my const gleich 3, and that thing should accept that because it's a const. Yeah, and as said, you can write a number, you can write a const variable, or you could write a some preprocessor definition that will be then replaced to numbers. The thing is, if we overwrite it here, what the compiler has done here when it encountered this line it said, okay, is it a const? Yes. Okay, so what is the const? The const is 3. So let's put the 3 here. And no matter how you change it, even if you change this memory region, no matter how you change it, you will never ever change what it will use for your array length. And in fact, if the compiler is configured to optimize your code, a lot of const variables might be completely optimized away. So the effect might be that because you did this, it will leave this in memory and you will be able to overwrite this address, but nothing that depends on this variable effectively in your program code will see the new value, because the reference to the variable for performance reasons during the optimization stages have been replaced with just the number 3 hard-coded then and there in the machine code. So I cannot even really nicely demonstrate it. Well, I can. Oh, I can. Another thing that you can use in C const x is the size of keyword, which just tells you the size of type. So if we make size of character, and if we assign it to a constant, it will actually evaluate. I already used x. Let's call it size. Sorry, it wants the type. This helps when it evaluates already the size. So if this would be, I think if this would not be a const, then it would not do it. Yeah. So it only if you make it a const, the compiler will actually look up. Not the compiler, the text editor, the ID basically will just look up what size is char, and it will tell you that. So we could also here put let's say my const. You can also write a variable. So now it's a 4 byte value, and if we put our array here, so it's 3 times 4, it's 12, so it should say 12, and it says 12. If we change this to 4, it will say 16. And and as you see, it doesn't matter what we write here in this using this trick. This will never have an effect, and this will behave the same way if the program gets compiled to machine code. This is why you really should not alter const variables this way. At least not ones that are defined in the function scope. So if the variable is part of a structure, then by the nature of things, let's say it should not be optimized away, even if it's defined const. So then you should be able to alter it, but then you could not use it for an array initialization, for example. But this is well, a small detour towards things you probably shouldn't do with variables. So during the next lecture, we will take a look on operators, so like assignment, multiplication, addition. I mean, we already took a small look on assignment, but we'll take a more detailed look in machine code. We will also take a look on the representation of floating point numbers, so how they are represented in memory. And what else? A few other convenient things, and probably the next time, yeah, of course, what are registers? This is also a very important thing. So now we have only touched on how these variables, which variables basically are natively understood by the CPU, but we have not yet spoken about how the CPU works with those variables. So that also will be a subject for the next lecture. Yeah, and I have 1 minute left, so I think that will be a good time to end today's lecture.